that can explain each other. And this is via the tumor instability. So let me remind you that the tumor instability is governed by the tumor Q parameter, which represents the competition between local pressure and rotation against local gravity. Q is above 1, the disk is stable. Q below 1, the disk is unstable. Observationally, it seems that galaxies tend to like the value of Q of about 1, slightly below, slightly above, but they tend to cluster about Q equals 1. These are high redshift galaxies by Genzel, 2014. Now, we can actually have a qualitative argument to explain why galaxies or star-forming disks like this value of Q equals 1. So let's look at it in a cartoonish way. This is Q versus time. This is the Q equals 1 line. And let's assume we have a galaxy, star-forming galaxy that starts with a value of Q slightly below 1. Then the disk is gravitationally unstable. We have asymmetries and clumps that starts to form. These, in turn, apply torques on the disk itself that drive mass transport inwards. The excess potential energy that is released during this transport can be converted to kinetic energy and drive turbulence. Also, in the dense clumps, we have stalled cell formation and therefore strong feedback. And from the supernova feedback, we can also drive turbulence. So transport and supernova feedback can drive turbulence, increasing the levels of velocity dispersion, and are able to bring Q above unity. Once Q goes above 1, the disk becomes stable. We have less clumps and less torques, weaker transport, weaker star formation. The driving of turbulence weakens. Turbulence is able to dissipate efficiently. Q goes below 1 again, and the cycle continues. So this qualitative picture hints at a mechanism that allows the disk to self-regulate at about Q equals 1, and it is doing so by the interplay between turbulence driving and turbulence dissipation. So turbulence is really a key process, both dynamically, but also in dictating the structural evolution of disks. And now, does this picture will hold water? So we've seen this before today. In 2018, Mark Humholtz et al. Developed a disk in equilibrium model in which turbulence dissipation is balanced by the driving by transport and feedback. And when compared to models in which one of the drivers is absent, either a model with no feedback or no transport, we can see that in terms of the velocity dispersion to star formation rate relation, the model in which feedback is driven by both transport and feedback is the one that best fits the observed relation. Furthermore, the model allows us to understand which driver is the important one for each level for the levels of velocity dispersion. So in order to achieve these high levels of velocity dispersion, we really need transport. And in order to achieve these low levels of velocity dispersion, we need supernova feedback. Moreover, the model allows us to understand, as a function of mass and redshift, which of the drivers is the dominant driver. So this is the evolution of 1 over the fraction of turbulence that is supported by supernova feedback as a function of redshift. And you can see that it's mostly a function of redshift. So high redshift disks tend to be mostly their turbulence tends to be mostly driven by transport, while in low redshifts, the turbulence tends to be more driven by feedback. Now the question is the whole picture. Are these all the drivers of turbulence that we have in disks? So let's think of other stuff that can supply energy to turbulence. So we talked about supernova feedback, we talked about transport. This is a small list of other potential drivers that may or may not be relevant. And today I want to focus on the role of cosmological accretion. Now the question of how important cosmological accretion is to the driving of turbulence has been asked multiple times in the past. So this is just a few papers that looked into this question. And these are the resolutions of each paper. So some papers say it can be relevant, some say it's marginally important, and some say it's completely unimportant to achieve the high levels of turbulence that we observe. The main thing that differentiates each of these studies is the assumed efficiency at which the accretion itself is able to convert its bulk kinetic energy into disk turbulence when joining the disk. And you can argue that using simple momentum conservation considerations or more complicated collision flow simulations, that in order for this efficiency to be high, you really need high density contrast between the two colliding flows. So do we have a reason to believe that cosmological accretion can achieve high density contrast with the disk? So this is 2 images we saw yesterday in Neil's talk, and we'll see more in Hans' talk next week, of simulations of idealized streams, cosmologically motivated idealized streams. And you can see that the streams, either with only cooling or only gravity, are able to survive through the hot halo, and on their way can fragment to form these dense columns, either by gravity or by cooling. So streams that feed the massive disks, especially at high redshifts, are predicted to be clumpy. When the streams are clumpy, we can have high density contrast with the disk, and therefore the streams, the accretion might have high efficiency at converting its kinetic energy to turbulence. So in light of this, we want to revisit the question of what is the role of accretion in driving turbulence when comparing to transport and feedback. So the way we're going to do this, we're going to use a disk in equilibrium model in which turbulence dissipation is balanced by driving, by multiple drivers. And we're going to assume that the disks remain in a state of marginal instability of Q of about 1. So these models have been used many times in the past, but only using partial potential drivers. And our goal today is to use accretion, feedback, and transport as potential drivers and to see which one is the dominant one as a function of mass and redshift. Okay. Teaser. So our model consists of two main equations. We have a mass bathtub equation. I'm sorry, my computer is not very good when it's not plugged in. So we have a mass bathtub equation and turbulence balance equation. This is the mass bathtub. Galaxies are assumed to be bathtubs inside dark matter halos. And by bathtub, I mean they're fed by sources and drained by sinks. So the source we consider is cosmological accretion of gas, which is proportional to the average cosmological accretion rate of dark matter. We have some efficiency, epsilon, which represents the fact that not all of the gas is able to eventually reach the galaxy. Not all of the galaxy that penetrates the halo is able to cool down and reach the galaxy. So this is the source term. And we have two sink terms. We have star formation rate, which we assume simple Kenniket-like relation. And we have mass transport, which drains the disk from its mass by moving mass from the outskirts down the potential well to form a bulge, which is a dynamically different component, and therefore we do not consider it to be a disk. So this is the mass bathtub equation. So the rate of change of gas is the sources minus the sinks. The next equation is the turbulence balance. So I'm writing it like this using characteristic timescales for the different other dissipation or driving. The dissipation of turbulence is usually a disk vertical crossing time. For marginally unstable disks, this is usually a disk dynamical time. So this is the dissipation of turbulence. So we talked about supernova feedback that can drive turbulence by moving its momentum by transferring the momentum from the bubbles to the surrounding ISM. This is characterized by this parameter P over M star, which represents the average momentum per stellar mass formed. This is for non-clustered supernovae, about 3,000 kilometers per second. For clustered supernovae, this is actually quite uncertain. Transport, this is how transport drives turbulence. It's inversely proportional to this parameter tau, which represents the efficiency at which transport occurs. This parameter depends on the different, on the actual mechanism that drives the transport, be it the encounters between clumps, dynamical friction, etc. And finally, accretion. The way we model how accretion drives turbulence is by assuming that some fraction psi a of the kinetic energy flux carried by the accreted material is converted into disk turbulence. Now, disk psi a will primarily depend on the clumpiness of the stream. However, it will also depend on the orientation of the stream, the geometry of the overall accretion, be it more spherical or cylindrical. Its value is quite unclear, and different studies assume different values for this parameter from very high to very low efficiencies. So for us, we look for a more qualitative understanding of the role of accretion. So we're going to assume quite ad hoc that this value is a simple linearly increasing function of redshift. Now, the exact parameterization, I cannot justify this, but The fact that Xi-A increases with redshift is motivated by a work done by Neil, which found that cosmological streams tend to they tend to fragment, and the mass fraction in dense clumps is an increasing function of redshift. There will also be a mass dependence, but we did not attempt to model that. Okay, so let me try and speed my computer up. Okay, so we are now ready to try and answer the question, which of the drivers is the more important one? So we look at this plane. The vertical axis is the ratio between the driving by transport to the driving by accretion. The horizontal axis is the ratio by driving by accretion to driving by transport. The plane is divided into 3 main regions, each in which a different driver is the dominant one, in terms of the amount of energy it injects into turbulence. So what we're going to do is we're going to see how galaxies evolve in this plane. So we're going to plot evolutionary tracks of galaxies in this plane and see where in the regions they live. Now, one of the most useful things about these bathtub models is that the evolution of a galaxy is uniquely determined by its host halo mass at redshift 0. So we can parameterize the evolutionary tracks that I'm going to put here by the host halo mass at redshift 0. However, not at all redshifts we expect galaxies to be disks. There's actually a finite halo mass range at which galaxies inside the dark matter halo is expected to be a disk. So the lower threshold is by a study we did a couple of years ago, where the disks are disrupted quickly due to frequent mergers. The upper threshold is where we expect the halos to host clusters, in which we do not expect the central galaxy to be a disk. So this shaded region, when the halo is in this shaded region, we expect the central galaxy to be a disk. And this shaded region here is transformed into the shaded region in this plane. So here are a couple of evolutionary tracks for different halo masses at redshift 0. These are how the galaxies evolve according to our model. And we can see that, for example, one galaxy which will end up at a 10 to the 13 halo mass, at high redshifts, the turbulence is mainly driven by accretion. And at some intermediate redshift, the turbulence turns into the region in which transport is the main driver, and it stays there until redshift 0. And for another galaxy, we have either transport or feedback being the main drivers. So I'm going to need 1 more minute. So we're going to throw a couple of more evolutionary tracks parameterized by the mass of the halo at redshift 0, and we can see a qualitative picture that emerges. So the model predicts that at high redshifts, accretion will be the dominant driver of turbulence in practically all of the disks. At intermediate redshifts, most of the disks will have the turbulence driven by transport. Maybe the low mass ones will be in the regime where feedback is important. And at low redshifts, we expect feedback to be the dominant driver. So we compared again to this figure I showed you in the beginning, the relation between the velocity dispersion and star formation rate relation as a function of redshift and mass. And we can see general qualitative agreement. So let me conclude now. So using a disk equilibrium model, we combined the driving of turbulence by feedback, accretion, feedback transport, and accretion with some efficiency. When this efficiency high, accretion is important to driving turbulence. And the clumpiness is really the key to drive this efficiency high. So high redshifts, accretion is the dominant one. Intermediate redshifts, mostly the massive ones, and low redshift, the feedback is the dominant one. And I haven't put any numbers here because the actual thresholds will depend on this parameterization. And the way we're going to study this and get more information is by simulations to see how it evolves with different parameters, the clumpiness of the stream, the orientation of the accretion, etc. And using analytical work, we want to take these parameters and put them in a cosmological context. That's it. Thank you.
Hi, very nice. So you mentioned earlier that in order to have kind of effective turbulence excitation, you need the high density contrast.
Yes.
And I can see how streams are much denser than, say, the volume filling CGM. But it seems to me that streams are probably less dense than the ISM. So I guess, yeah, what kind of density contrast do you need? And
So,
And what do you think is realized for streams versus the ISM?
So, so the key is the clumpiness. When the disk is very clumpy, you expect the clumps to be more dense than the disk. So if the stream is extremely clumpy, now the actual density contrast, if you just use simple momentum conservation, you don't need very high density contrast to convert more than 50% of the kinetic energy to turbulence. If you look at more, the complicated simulations of colliding flows, then you might need slightly larger density contrast than around unity. But if the streams are clumpy, you expect them to be much more denser than the ISM.
Okay, thanks.
One more question, and could the next speaker go ahead and please approach the front?
Yes, how does this radial transport differ from just the processes that occurred in a normal accretion disk around a massive object?
They're actually very similar. They are both driven by the asymmetries that occurs due to the tumor instability or other instability. So if you look at the papers by Avishai or by Turbulence and Burkert, you see that they usually use very similar considerations as a viscous accretion disk, or the work by Gami and etc. So it's a similar process, just on a larger scale. And actually, one of the main differences is the fact that in accretion, that you have highly supersonic turbulence in the galactic disks, when accretion disks, I think, are usually more transonic. So that may be a slight difference.
Frank?
I have a related question, and I'm trying to understand how transport causes turbulence. Right? In an accretion disk, it's the turbulence that leads to a viscosity, and that leads to transport. I mean, transport, if you think in terms of a dynamical friction acting on clumps, that just causes a little bit of compression, large-scale distortions of the gas that act as torque. I don't see how I get turbulence out of that. How do I get vorticity?
No, the main source is the gravitational potential energy. When the mass moves from the outskirts of the disk to the center of the disk, you have this excess of potential energy.
Yeah, but it doesn't have to go in a turbulent way. I can displace gas smoothly when the gas comes in. Why does it have to be turbulent?
If you look at models, so this is one of the main work so if you look at the work done by Turbulence and Burkert 2010, and they show that the velocity dispersion goes up as a result of this excess potential energy. If you look at if you actually looked at the hydrodynamical equations, assuming supersonic turbulence, you need to make some more assumptions, but you see that the level of velocity dispersion is brought up by this delta of potential energy. So the interaction between the inflowing material and the disk, I don't think we know the exact, precise mechanism that really causes but this is the idea, at least.
Let's thank Omri again.